talk about games. Just a quick vibe check of the room. Like, how many people got their start into programming because they wanted to make games? It's a fair amount. Okay, how many of you, like, on a daily basis are, like, making games, or at least, like, once a week you do something of a game? Okay, cool. A bit less than the first wave. Which is it's a common story. People start programming to make games, but then you turn into an adult and you get like a job in North Virginia consulting on JavaScript. And you stare in the mirror, and then your like 14-year-old self is looking back at you, and it's like, "Are you making games now?" And you're like, "No, and punk rock is dead." So that's my target. For all of you who wanted to make games, you now have the ability. You could just do it. So it's gonna be like a 30-minute speed run for like the very basics, and it's gonna be no engine. We're just gonna use simple tools, so you don't have to learn anything. I want people to be able to just use the skills that you have. Cool. I'm Tony, by the way. I'm not on social media, so people always ask like how they can reach out to me after these. There's a game development channel in DC Tech Slack, so if you need to get in touch with me, that's the way to do it. I always go by Tony, and my profile picture is always this picture of Shio Gorath from Elder Scrolls, but he's like in a Gucci belt and Louis drip. So I keep it consistent. Cool, art creds, because you're gonna see a lot of awesome pixel art in this presentation. None of it's by me. All my art I use from a great creator, Pixel Frog on itch.io. All his stuff is both free and public domain, which makes it super easy to use in presentations without worrying I'm breaking the law. Do support them with donations if you ever use their stuff though. Same with Kenny, free public domain. They do it to support amateur game devs like me. Yeah, let's get into it. So engineless game dev, we're still going to use tools. It's kind of like libraries over frameworks. I'm going to introduce you to something called tiled, and I'm going to introduce you to a pattern called ECS. So just with those two, you should be good. It'll be a more comfortable working environment. You're not learning to make a game engine. You're just going to have some tools, and by that, you could just intuit how to make a game. If you want something more involved, Phaser, just use Phaser. It's a great JavaScript engine. The rendering engine I'm going to use was actually originally Phaser's rendered engine, and then I got forked and moved into that. You have options though. So what are we going to use to make our games? It's Pixie.js. I call this the rectangle rendering machine. The fundamental building block of 2D games is I want to take a rectangle from this image and I want to put this rectangle onto the screen somewhere. And then you move around the rectangles and there's a game. So this is the minimum layer that you're going to need unless you want to start writing fragment and vertex shaders. So I'm keeping to my promise, no engine, but we do need some kind of rendering library, or this is going to be a WebGL talk. Which would be cool one day, but I got 30 minutes, so. So this is Hello World in Pixie.js. Don't worry about reading the code. This is mostly ripped from the Pixie.js website. And it is what I just explained. I load a texture. I say, here's a URL, give me an image. And then I add it to the stage, and I say, here's your X coordinate, here's your Y coordinate. And then in a game loop, I say, add half an integer to the X coordinate, half an integer to a Y coordinate. Now we have a moving T-posing bunny. That's Hello World for any game engine I do it. Just make sure you can render something, make sure you can move it around. But this kind of sucks in aggregate. No one wants to play this game. We want to make like a cool world. So we want something like this. This looks interesting. Once again, art by Pixel Frog. I love how the sheep just like bounce like that. They have more animations, but I made that their idle animation. There's a couple problems with this going from the bunny to this, right? This is a lot of squares. Like, I think this is like a 64 by 64 grid. And then there's layers. So 64 times 64 times, I think I have like 4 layers of elevation here. You don't want to manually write X and Y coordinates from all of this. You'll go insane. So how are we going to solve this problem? We're just going to use sprite sheets. Sprite sheets mean instead of loading 500 images, we can load one that just packs all our images together. Every game engine does this. It would just like it would be ridiculous to work without these. But now we need a way to talk about these sprite sheets in a way that we could do write the bunny to the screen. Obviously, I don't want to write all of these. We need a coordinate system so we can talk about these, right? And here's the coordinate system that Pixie.js uses. Pretty much every other game engine is going to use a different coordinate system that has a different origin. Sometimes it's in the center of the rectangle, sometimes it's in the bottom left. Pixie.js is top left. So the x-coordinate for any animated sprite in Pixie.js is going to be how many pixels from the top left do you have to move left. And then the y-coordinate is how many pixels from the top to the bottom. And then you have width and height. So you don't have x1, x2, you don't have y1, y2, you have xy, width and height. And you can see me drawing it here. So that purple line, that's me drawing out 32 pixels. Red goes down 32 pixels, and then I expand out with that, that white select box. And that's a frame. I can now talk about a portion of this sprite sheet in a way that the engine's going to understand. Still have a problem though, like, okay, am I going to write out a frame for every sprite? That would really suck, and we would have our original problem of being way too slow, right? So this is where the next tool that we're going to use comes in. And the cool thing about this is if you don't want to use this, you could just use a Microsoft Excel spreadsheet and manually punch numbers in, because I like to call this my level editor, but also like glorified CSV file producer. It's great, it's free, it works on every operating system. You can still use a CSV file if you want, but so we can feed this a sprite sheet and we can tell something about, sorry, not a sprite sheet, a tile set. And we can give it some information about it. So I'm going to take this sprite sheet and I'm going to tell tile, hey, this has 12 columns. And I'm going to tell it the tile width and the tile height. It'll give me the tile count. We don't need that. Now with just this information, we can actually generate a frame for every single part of this image. We have enough to actually run this through. And I want to call the top left tile, that's 0. Then the next one is 1, 2, 3, 4. We'll wrap around. And this will go from like 0 to 131. That would be awesome, because then if I could refer to all these sections of the sprite sheets as numbers, well, then I can just make a CSV file and that will be my map, and that's where we're going to. So what would the x-coordinate of any given tile here be? This is a pretty simple formula for that. It's just the index of the tile, counting from 0 to how many tiles you have, divided by columns, and that's the remainder of that division. Y-coordinate is, once again, just the index of that tile divided by columns, and just rounded. So you just have the product of the division and the remainder. And I actually have here's me applying that algorithm to this. This is literally like just 10 lines of code. You don't have to remember this. You'll be able to intuit this. Once you know that coordinate system, you could just write this. But you saw that familiar frame data structure. We got X, Y, W, and H. And we can apply it to the tile set, and it kind of looks like this. See, as the numbers go, 0, 1, 2, 3, 4, it's being plugged into the algorithm, and now we have a frame for every tile. Every tile has those 4 coordinates that we can use, and we have a number that can go along with every one of them. Awesome. We can now start making levels. We're getting close to the bouncy sheep now. So now that we have numbers for each of these tiles, this is what a map looks like. It's just a CSV file. So you can use tiled to give you like a visual of what you're doing here. Otherwise, you have to remember like, oh, 1 is grass, 27 is the corner piece of the cliff. You could do it, it's hard. But we basically run that algorithm, we put everything into a dictionary that is number of the tile index, and then the key is just that sprite sheet frame. And now we just send this to Pixie and we say, here's your sprite sheet, I want you to render whatever number comes up here. And also you notice again, this is not an array that has columns in it. You have to use the width. So it's just one array, and you have to intuit that when you hit the width, same formula, x coordinate is going to be the remainder of the division between your index and the width. Y coordinate is just the division rounded to the nearest integer. And so we can actually see that being applied. This isn't an animation that I rigged up. This is actually like just the 2 pieces of code I have running in Pixie.js against that map you saw. This is how simple it is to do. And cool, now we can build a world from all these pieces. This actually looks more exciting to like explore around in. And that's a start. I recommend everyone, when you start making a game, get to the point where you have like a world that you're excited to explore, then start putting stuff into it. And now we're gonna go to that. So this is where everyone gets stuck. It's, okay, what do I do now? Like, I want rules, I want collisions, I want people to be able to like swing a sword and it hits a goblin, and the goblin says, ouch. And one way of doing that without using an engine is this thing called an entity component system. If you search around this, you're going to get a lot of libraries for this. You really don't need a library to implement this. You could just use JavaScript, TypeScript. It's extremely simple. But it is being adapted by a lot of engines. Like this bottom text I got from Unity. And it's like, entity component system is game code based on ECS, can quickly adapt to major gameplay changes. The great thing about an entity component system is how isolated systems are. So all of you have jobs, presumably, hopefully. If you're gonna make a game in your spare time, you're gonna start something, you're gonna peace out for 2 weeks, not work on it, and then you're gonna fire it up again and be in an unfamiliar code base. You want to get to the point where adding a feature to your game does not involve you editing pre-existing code. And an entity component system, I believe, is the best way to say, hey, I want a new feature, and all the code you add from there is additive. That's why I recommend it, and that's why I exclusively use it, because that's what I do. I start a game and I peace out for months on end. So entity component systems are odd in that entity is probably not what you think it is. Entity, when you look at any other game engine, is going to be this huge struct with all the things in that struct. It'll have position, velocity, whether it has a collision box. What's its health? If it has health, what is this current animation? If it has a current animation, what frame of the animation is it playing, and how many milliseconds has it been playing that frame for, because you need to advance to the next frame if it reaches a certain threshold. You get these mega structs. In an entity component system, we don't have that. So in an entity component system, you have a scene, and your scene is just all your components, but they're all these big arrays. And this is really a fixed size array. So what you're looking at when I make a typical game, your array is going to be like 5,000 entities that you've decided can exist in your game. And they're nullable because they're really slots. So velocity will be an array of 5,000 items that will either be an empty slot null, or it will be the has velocity component. You can probably intuit what I mean by velocity. It means x change, y change, position, your x coordinate, your y coordinate, et cetera, et cetera. This is different. You might naively, if like you just went to start, you would just have this array of entities, and each entities just have all their own attribute. But we want to get away from that, because once again, when we come back to this project after 2 weeks of not working on it, we want a way to just say, I want to add a unique system. I'm not going to edit any existing structs. So components should really be the bare minimum of data that you can possibly get where you're not separating things that make no sense on their own. X, Y, cool, you need them. You can't really communicate velocity with just X or just Y unless you're a one-dimensional being or something. So I would say that's a component. Would I add collision box? Does everything that have velocity necessarily mean it's going to run into something else? No. And that's really what we want to get away from, that hierarchy of object-oriented programming where we have to make these philosophical decisions early on. Oh, the velocity component extends from something that has positions, but maybe something could have velocity without a position, I don't know. But that's what we mean when we have components in an entity component system. These very, very small structures, and then these arrays that span out from them. Then what's a system? How do we actually act on this scene in order to make stuff happen? Pretty simple. This is not an example that's been dumbed down. If I'm going to do a velocity system, it's going to work like this. So we have that scene that has these this giant array of velocities, this giant array of positions. And we're just going to iterate through all the entities in that scene. And we're going to say, hey, if we have a velocity and we have a position, and neither of them are null, because remember, they're slots, then we're going to do something. That's how they interact. So that's how I get things to move. I say you have a velocity and you have a position. If you have both every tick of the game, I add them together. Pretty simple. And once again, with your scenes, you want to get this mental list of these are the things that an entity needs to have in order for this system to take effect on it. There's a better way to illustrate this. I figured I really need to animate this to kind of drive it home because it's kind of abstract. But we can think of it like this, right? So you see these grayed out buttons, those we can say they're the null slots. There's nothing there. And then the blue raised button, well, that's something that has it. And the symbol you see is the different component. These are random icons, but hey, there's a sound icon, maybe this entity has sound. There's a gear icon, maybe this entity is configurable. And then what are the systems in this diagram? Well, the systems are these sliding selectors that you see going back and forth. Sometimes a system only requires that you have one of the components. We would say it activates when it hits any component that's raised. If you see something that's 3, well then it would only be activating when all 3 components that are lined up are blue. This is an entity component system being animated in an entity component system. This is actually Pixie.js running, or at least a GIF of it that I stuffed into a PowerPoint slide. So we know what systems are, we know what our components are, but okay, what's an entity? We don't really have an entity. An entity is literally just an index. If components are these arrays that have to line up with each other for a system to activate on it, well, I'd say an entity is just 7 or 8 or 0. And in this way, I could say, okay, player, you're 0. You have all those blue components in the 0 row, and any system that lines up on you will act on you. But I also put a GUID here. This is important to note because this will bite you. I mentioned the arrays have a fixed length. So when we spawn an entity, we're going to get whatever's not being used in those arrays. Cool. But it's fixed, so when we're done with an entity, we need to put it back. Cool. That means we're going to reuse its index. So let's say you have another entity that refers to another entity. I'm entity 1, I'm following number 7. Entity number 7 dies, goes away. The other entity is still following number 7. We can now reuse number 7 for a different entity, and suddenly it's following something entirely different. So in any entity component system implementation, apart from the index that tells you where to find the components for this entity, there will be a unique identifier. So I say, if one entity refers to another entity, you must store both its index, so you can find its data, and its GUID. And anytime you refer to it, it's that entity's responsibility to check if the GUID is the same. The GUID is always new. So if you're referring to entity 7 with GUID 2662, and you see another entity, ID 7, with some other GUID, you know, drop that, stop following this. They're gone. The entity that I thought was there is no longer there. For this, you're going to usually need some kind of pool, right? You need something to track what indexes you're allowed to use and what indexes are taken up. Because you can't just assume that an entity with no components, all null, that it's not being used. Maybe it will have components later. The only way to check is really like keep a pool of array indexes and track which ones are in use and which ones aren't. And this looks a lot like a memory allocator. Like, yeah, we're writing C now. We have alloc entity and free entity. It's almost like a real programming language now. And then the last is verify entity, because your pool can also map which indexes align with the GUID that was given out. So when your pool allocates an entity, it generates a GUID, and then it says entity 7 needs to have this GUID. If not, it's an imposter. So now we can verify entities. You'll usually just need like some kind of mechanism like this. So what does constructing an entity look like? We have no new class keyword, right? It's straightforward. We take in the scene which has the big list of arrays. We'll use our entity pool to get an ID that we could use. And then we go for the scene arrays, and we're going to set at the entity index, that's the slot that's been allocated for us, all the different components. And now we have the entity we want. And what you'll find is, like, as you're using an entity component system are these like moments of delight where you have all your systems in place and you're like, I want to add this functionality. And all you do is go to the spawn code and you say, okay, you no longer just have velocity, sprite, and position, but you also have like gravity now. I've decided you could fly, and you just add the component here and it just works in your world. You start to think of your game as these are the different attributes things can have, and your systems are like the laws of physics, and it will just take over and it will kind of start to just do what you expect things to do. Cool. That's the end of my spiel. These are several unfinished games I've made using entity component systems. And that's the homework I assign you all. Go home, make games. Make small ones that fail fast, because there's not much of a science behind this right now. GameDev is a lot of game developers talking to each other and saying what worked and what didn't work. The GUID idea, I had to have other people tell that to me. You'd be shocked that when you go to someone and describe a problem, that someone making an entirely different game will have the exact same problem that you're having. And particularly with entity component systems, you'll find you can actually reuse code among different games with other games. Like, once again, that velocity system, I just copy and paste everywhere. Otherwise, if you start like with a from scratch outfit, you find yourself re-implementing everything over and over. That's it. All right.